Hello everyone, I'm Jean-Baptiste Bénard and I'm working on the monitoring infrastructure in the Admire project. And today I'm going to present you in more details the developments we have made specifically for the monitoring infrastructure. In more details, the goal was to be able to monitor malleable application. This morning we have been explained to what is a malleable application. It has some peculiarities. In particular, it's an application which changes shape over time, as malleable does. The reason for malleability is also driving the nature of the measurement we will have to do. There are multiple reasons to be malleable. First, you may want, of course, to optimize computation, as we have seen, minimize the wait times, time to machine, or maximize the machine utilization, meaning you want your machine to be full, and jobs which are potentially small to enter quickly in the machine. And the last case is to lower power. So this variety of scenario means that we need to measure a lot of different things to provide the model guiding the malleability, because as we have seen, Admire is about a feedback loop, controlling the application and optimizing them over time. So in terms of measurement, what does it mean? Because what I'm going to present you is the metric proxy, which is the measurement infrastructure for Admire. It means we need data over time because we want the application to live over time. Time is a challenging dimension when you consider performance measurement because it's very verbose. Second thing, we want to adapt the application in function of its balance, which means that we have to measure also over space. Otherwise, you cannot characterize imbalance if you cannot compare how the processes behave through the machine. And also, last case, as I will further illustrate in the presentation, we want to have a model for each program, meaning we want to track the various execution and quantify how they run and how they behave on the machine in order to generate a corresponding performance model. Here overall, we have all the dimensions, so we need to keep all the dimensions. So this is why I've put this challenging flag, is because we need to measure in a relatively verbose manner. The difference of what generally performance tools in high-performance computing do, which do profiles, which summarize one or multiple dimension. A profile is without the temporal dimension and potentially without the spatial dimension. So I made this slide to illustrate why we want to have malleability at first. I'm trying to show you why a performance model matters. Here you have the Rodinia LU OpenMP benchmark, and we scale it from one thread to 128 thread. The colors for the complete line are the various problem size, and then we scale it. And the dashed lines are providing you the efficiency limits. So this is the efficiency over number of threads. So the point line here is full efficiency, and here the dashed line is 50% efficiency. As expected, when you scale a parallel problem, so this is strong scaling here, you lose efficiency because the parallel overhead increases. As the parallel overhead increases, there is a point where the application is less efficient. And this is what we try to catch in our performance model. So you see, we have to measure multiple jobs because we have to find over all this 128 execution, we have to compare them because this is a transitive metric, which is defined as the sequential time versus the parallel time. So where do we put the sweet spot? How do we cut? This is the one of the thematic of Admire. Here, the example is called moldability. So this is the principle of changing the configuration at launch time, whereas malleability is during runtime. Just a small definition. So recall of the Admire feedback loop. So it's a very simple story for monitoring. We have a program, we run it in a given configuration. The execution will generate a given set of performance metrics, performance results. And then this data can be used to generate models. The models will then allow to reconfigure the application during execution, or also to define what is a good configuration for the future execution. If we look at the bottom, we have a more verbose view of the infrastructure, where you have the application, the monitoring, and the modeling. These are the two components which are part of the monitoring part in the Admire infrastructure. So with the monitoring, we will generate the model, and this model will feed the intelligent controller, which is the central component in the Admire infrastructure. And this component will then take malleability decisions. This will be explained in details in the future talks later this afternoon. So we have to choose the right measurement granularity. So as I mentioned, we wanted a bit of everything. So because we wanted to be verbose, and we also wanted to be with a reduced overhead. The consequence is that our measurement infrastructure is capable of generating a wide variety of artifacts, ranging from a profile, which reduces over space and time, and also to a performance trace, which is storing all the events. As I will show you, the performance traces we have retained do not store events indefinitely. They can be resampled over time, but more detail on this later on. The tree-based overlay network is provided by UC3M, University of Madrid, and it reduces data over space with a very high frequency in time, which allows us to have a global view of the machine very efficiently. Eventually, we have dynamic profiles, which are profiles over time with a predefined frequency. Now, if we look at the architecture of the monitoring infrastructure, we have one daemon running on each node. And this daemon, called the metric proxy, is in charge of capturing the data coming from the various processes. One problem in our approach was that the processes are potentially short-lived. So short-lived, it means when you run MPI processes a given job, it starts and it ends. And initially, we consider the Prometheus approach. So Prometheus is scrapping the various processes. And by scrapping the various processes, it means it had to do HTTP request to get the data in. If the corpus of processes change a lot over time, it's not practical anymore to have a pure Prometheus approach. This is why we developed the metric proxy, which is an aggregating push gateway for Prometheus. And thanks to this, the program pushes their data in the metric proxy, and it is then aggregated over space and time to generate the various time series, the profiles, and the global state of the machine. If we look more closely at the architecture, we have the metric proxy running on each node. We have MPI processes which can be collected, the node state, and also the storage state. All this is collected using a Unix process. So it means we don't use HTTP request. The data provider do send their data in a streaming fashion and with regular sampling. We also support regular Prometheus exporters, meaning that we can send HTTP requests, for example, to a node exporter or an existing Lustre exporter for Prometheus. It is also the case in the Admire infrastructure that the ad hoc storage will expose their data through this, and these data are then sent to the metric proxy. The metric proxy are shaped in a T-bone using limitless, and these data are then projected to various views that I will show you later on in the interface. These views are intended programmatically to the intelligent controller to do the malleability decision. Thus, if we have a closer look at the interface, I mean the content of the metric proxy, you have, as I mentioned, the Unix server. If you have an HTTP client which is able to scrape, so it is a Prometheus vocabulary to consume data from a remote data source, to scrape either other metric proxy or Prometheus exporters. All these metrics are stored per jobs in a big array of data, and then these metrics are projected to the various analysis modules. Eventually, on the other end, we have an HTTP server which allows you to consume this analysis and to forward them to the intelligent controller. We have then HTTP interface, and also we can have Mercury interface to RPC, which is in development. So looking at the implementation, it's relatively simple. We had the first prototype in C, and then we moved on to Rust because we wanted to have more interfaces and more development efficiency and also reliability of the code, because the Admire infrastructure is made to be always on. It means we have to constantly run, and Rust is more stable on this aspect for memory management. Thus, we have a Unix socket sending data from the client library, which is also in Rust, featuring a C interface. And here, these are the data producers. This could be, for example, an MPI process where you have the instrumentation layer preloaded and generating the events over time, and then the counter are sent progressively. Let's now have a look at the interface. So this is the landing page on the HTTP endpoint of the metric proxy. And if we look at it, you have several tabs, which are just a finally user interface. It's not intended to be used this way in the Admire project because we want to automate it. Here you have the potential topology of the proxies. So proxies, as I mentioned, are built as on a T-bone, and when we start the proxy, they pivot. So it's an expression to say they connect on the root process, and then we define a binary tree, which reduces the data up to produce a global view of the machine. Here you see the scrapes of the root process, and the root process, and we scrape its two child nodes, so it's scalable configuration. Thanks to this infrastructure, we are able to do real-time job tracking because you see a process joining the tree on one of the proxy, and it shows up in this proxy, and the data from the job are then reduced to the root, and it shows in the root. This allows us to have a dynamic view of the jobs running on the machine, giving us tracking of the various performance data. What is inside this, I will show you in the demo soon, is that when you click, you have the various metrics for the given job. And these various metrics allows you to understand how it behaves. We don't store the jobs as they run because of storage constraints. So job details, as I just mentioned. Here you have a trace. So a trace, it is just the storage of the various profiles over time, but it is a resample trace because we cannot afford storing a full trace of a long running job. So we limited it to 32 megabytes per job. And then as I show here, you accumulate various points. But when you hit the limit, how does it work? So here you have a period of 1 second per sample. So the sample will accumulate until we hit the 32 megabytes limit, which is arbitrary. And then we have to resample the trace. So as it is profiled, there are summative values. And so we sum up, and then we have freed half of the buffer, around half of it, because not all metrics necessarily are all in all the snapshots. But this allows us to dynamically adapt the sampling period, because once you resample, divide by 2 the trace, you also multiply by 2 the sampling period. This allows you to, to fill the buffer in a slower manner. And we repeat the process as the long-running job continues. Here is a visual illustration of this process. So on the left, you have the initial trace with the first sampling. And on the right, you see that we resample the trace using very simple linear interpolation. So we have less points, but we still have the general view of the data. When a job finishes, it is a set of counters, and it is stored in what we call the profile store. The profile store is for each command line, the various runs which are associated to it, with, of course, the performance data stored inside. With these various profiles, we use XtraP, which is, as its name sounds, an extrapolation tool to extrapolate the value of the profiles in other configurations. So what happens is that you see you have multiple jobs, which are then generating profiles. All these profiles are sent to an XtraP model file, and this model file is then fed to XtraP, which then will yield a projected profile. A projected profile is simply the execution in an unknown configuration, given the interpolation of the various metrics. You see that this can be used to infer how this job would behave on a size we have not run yet, on a configuration we don't. So we'll have a presentation dedicated to this tool later in the day. I wanted to mention the Prometheus integration. So as I mentioned, we have a tree-based overlay network with limitless, and we can feed a Prometheus instance. So it is the regular Prometheus instance which predated the project. But we have to scrape only the root proxy, because the metric proxy itself provides a /metrics endpoint, which can be scrapped by Prometheus. This allows to have a temporal storage of the various events in the full behavior of the machine. And of course, once you are in Prometheus, you can have the view from Prometheus, which are well known and classical. Here you have the view inside the embedded web server for Prometheus. At top, you have the total bandwidth for various MPI functions. So this was like 5,010 nodes. And in the bottom, you have the syscall write bandwidth per node. So you see the kind of projections we can do using these features. And of course, once you are in Prometheus, you can easily have a graph and a view. So this view is courtesy of Ahmad, which we'll present later on. He made the dashboard, but at least I can show you that we can go to a higher level of representation. Little overhead assessment. I have to say that it is on the first version in C, but as we have the same layout, we expect the similar overhead with the Rust version. So sorry for not showing the final results. But what we see here is that for a measurement period higher than 4, so this is the frequency at which we push the data in the proxy, we have an overhead which is relatively the machine noise. So the two dash lines here show how long it took to run in average, min-max, so min-max. So you see, we are relatively in the range. On the right, you have the overhead for instrumenting MPI command, which is a very small MPI function. And here you see that we were around 60 nanoseconds, so it's relatively reduced overhead per code. So the source code is on my GitHub, so feel free to have a look. It's not a final release, it's a bit of work in progress, but we will document and make a first release soon. And so I wanted to show you a quick demo. Okay, so let me start the proxy. So here I started the proxy, and you see that I have the interface here. I have two jobs by default, which is main, which is the sum of everything. And also, I also have a per node job. So this is the name of my machine. If I click on the job of this machine, I can see the counters updating in the various proxies. And now, let's say I want to start an MPI job. So I think I have it in my history. So I start an MPI job. This job is doing barriers like crazy. And you see that it has popped here. We can check that it was doing barriers. So here you see the barriers updating. Sorry, let me make it larger. Yep. So a lot of barriers happening here. So it's one view. So it's the profile view. And here you also, of course, also can have the trace view. Let me maybe reduce, it will be easier to see because I'm very bad at CSS. Profile view, and you can translate it to a rate of barrier. So it just derivates the signal, and you can see that if I start a CPU consuming thing, it's just yes, the rate should lower, I suppose, because I steal some cycle from MPI. And if I stop it, it should become the same. Yes, so the application stopped just before I stopped it, but here you can see the idea of this tracking. I also wanted to mention that we can scrape regular Prometheus exporter. So here I have a join command to join to localhost 9100, which is the node exporter for Prometheus, so standard one. Here my JSON endpoint says it is happy. And if I go to the scrapes, so proxy topology, you see that I'm now scraping localhost 9100 very fast. I don't know why the period is 0. Maybe we want a lot of data. But hopefully we should see all the node counters coming in. So now we have many more counters than before because I'm scrapping the node exporter with a lot of data. And we can do the same for the various metrics. When a job finishes, it will generate a profile. So let me generate more jobs. I have a command doing a sex, maybe 1000 is a bit crazy. I don't want to turn the demo effect. So I will just run hostname. And here you should see the host name popping in. So it's 100 jobs, but so you see they are gathered by command. It's not ideal because we need to, an HPC application not necessarily has a command which changes for its input, but this is how we gather them right now. And here you can see the various programs with their final data, and they also will show up, of course, in the trace view. Yes, and we can set alarms, but you can ask questions on this if you. Okay, so I already read the conclusion, so we have time for questions. So I presented you the Admire proxy with a small demo. So what it is? It is an aggregating push gateway for Prometheus with some extra feature linked to HPC, so the ability to quickly collect metrics from short-running programs and such. We implemented it in Rust with a lot of advantages in terms of implementation. We have no machine one monitoring capabilities. So we are able to generate profiles of all the jobs, real-time tracking of the jobs, traces of these jobs. And we tried it with 0.5 second resolution at scale. So it was 60 nodes. So we had the data flowing it towards us. We are currently working on modeling capabilities, which is the final step of the project. So integrating in the whole Admire infrastructure, particularly with XtraP that will be presented to you later, because we want to automate the model generation. And also with FTIO, which is a frequency analysis of the performance signals that we also want to integrate over the traces we have with the monitoring infrastructure. So the program is a bit work in progress, so my GitHub does not even have a README, but soon we will make a first release when we will have validated it at scale correctly. It's a question of a few weeks. But at least you can look at what it does and how it's made on the GitHub. Also, we do the test at scale thanks to University of Torino, so thanks to them for providing the hardware for the Admire project. And so that's already the end of my presentation, and I can answer questions or such if we have. I don't know if they are relevant.
Not see a question.
No?
No.
Okay.
No raise the hand. Yeah, I see raise the hand.
Yeah, Jean-Thomas.
I have one question. So when you display a total value, the counters are very high, and many counters are at zero.
Yes.
It's expected. Is it possible to show on the total one with high value, like so?
Yeah, I see. I made this because I did not want people in the project to say that I don't measure anything. So this way I show all the counters which are zero. It is just a filter in a map to hide them. But I agree they are not sorted at all. It's which I just throw everything that I could measure. Because when the interface for the collection library starts, you register all the counters and then you increment them and such that they show as zero. So yes. But they are not stored in the trace as zero. So only varying counters are stored in the trace. So just a presentation glitch, I would say. Yes?
Just curious about the selection of Rust as programming language.
Yes.
Just not in the main scope of the project.
Yes.
So the reason was the avoiding memory leaks, or?
I think it was speed, because we had the first version in C, but we needed more features to help the integration of the project, particularly the web interface I have shown you. Doing it in C would have cost long development. And here in Rust, you have the crates mechanism, which is sort of libraries which are statically linked. And with this mechanism, we were able to collect more tools like an embedded web server. It's a question of a few lines in Rust, whereas in C, it was more complex. Same for HTTP request. The initial version in C was doing HTTP request manually. So we were writing get in the socket. Here it's more elegant, and we are ready to have TLS, HTTPS, so to go to a more production-ready implementation, which would have been more costly in C. And so I have no regret on choosing Rust. Also, it was an excuse to learn Rust for this. This is the selfish part. Yeah.
Thank you.
Other question? Thank you very much.